Assalamualaikum and hi everyone. We are from Group 5 from Section 12 and today we are going to present our group project which the title is Rate of Change. So these are the group members for Group 5. The first one we have Muhammad Hakimi bin Muhammad Helmi, Muhammad Sharif bin Muhammad Mubarak Ali, Adlin Nurliana binti Shamsul and I, Siti Hazira binti Ramli.
Hi, Assalamualaikum, and my name is Adlin Nurliana binti Shamsul, and now I'll present about introduction. In civil engineering, it's important to know how variables change to design safe and efficient structures. It can be calculated using concept rate of change. This helps engineers analyze the for example, the traffic flow, material stress, fluid velocity, and environmental change over time. Rate of change represented by using differentiation method, which is rate of change equal to dy over dx. For single variable, y equals to fx, we represent the differentiate by dy over dt equals to dy over dx multiplied to dx over dt. So next, for the two variable, for example, z equal to f x y. That represent the dx over dt equals to dz over dx multiplied to dx over dt plus dx over dy multiplied to dy over dt. And now I will pass to the next representer.
Okay, let's move on to the problem statement. Our problem is a pressurized spherical gas tank is being filled up with a nitrogen gas. After 10 seconds, the volume of the gas inside the tank increased by 2000. So we have three questions that need to be solved. The first, find the rate at which the gas is filling per second. Next, calculate the rate at which the radius of the tank is expanding when its radius is 50 cm. And the last one, determine how fast the internal surface area of the tank is increasing at the moment when its radius is 50 cm.
Next, in order to analyze the rate of change of a pressurized spherical gas tank being filled with nitrogen gas, there are three objectives that we observe. The first one is to identify the gas rate of change over time. The second one is to identify how fast the radius of a sphere is changing. And the last one is to evaluate the rate of change of surface area of a sphere respect to time.
So next, I'll present about filler table. The first one, fact. A spherical gas tank is being filled with nitrogen gas. The idea, it can apply differentiation to find how much the gas is filling per second. Learning issue, it's learned how to apply related rate using differentiation. For our action, we calculate the dV over dt by dividing the change in volume by giving time interval. For the second one, the fact that we know is volume of sphere is V equals to 4 over 3 pi r power of 3. Using the idea that we know, I use differentiation of VR to calculate the rate of change of radius when r equals to 50 cm. Learning issue for this fact is understand the relationship between volume, radius, and surface area of the sphere. The action that we do is differentiation V equals to 4 over 3 pi r power of 3 to dr over dt. Then we substitute the r equals to 50 cm and dv over dt into the equation to solve for dr over dt. So the third one, we know the fact that surface area is A equals to 4 pi r power of 2. So the idea that we do is evaluate the rate of change of the A when the radius change at r equals to 50 cm. The learning issue that we learn is to substitute the volume correctly to solve for unknown rate. The last one, for the action, we differentiate the surface area and insert the value of r equals to 50 cm to determine dA over dt. So That's all for the filler table. I will pass to the next presenter.
Now, I am going to present the literature review that we researched. Students across various age groups struggle to grasp the concept of rate of change. According to Avgarinos et al., average rate of change corresponds to the ratio of differences or the slope between 2 points, whereas the instantaneous rate of change is represented by the derivative at a specific point. Orton 1983 found that the confusion between several important ideas related to rate of change, such as confusion between the rate of change for a straight line and the rate of change for a curved line. James Chen described the percentage change in value over a defined period of time, which is a momentum of a variable. Simulations of real-world speed scenarios automatically connected to corresponding graphical, numerical, and also symbolic representations was explored to support the development of a deeper understanding of the concept of rate of change. And this is found by Herbert and Pierce in 2008.
Now, I'll explain the methodology. This study uses related rates to analyze how gas volume, radius, and surface area changes over time in a spherical gas tank. Differentiation techniques are applied to relate rate of gas inflow, rate of radius expansion, and rate of surface area increase. The key equation used in this project is first volume, which is volume of a sphere is 4 over 3 pi r cube, and surface area, which is pi r squared. By applying the chain rule, the relationship between these variables are explored to predict structural expansion. This approach helps ensure safe gas storage by monitoring volume, radius growth, and surface variation. Moving up next to the calculation. Question A. A pressurized spherical gas tank is being filled up with nitrogen gas. After 10 seconds, the volume of the gas inside the tank increased by 2000 cm cube. So, to calculate this, we know that the dV is equals to 2000 cm cube and the dt is 10 seconds. So, we just divide to get the dV over dt. Since dV is 2000, we just divide it by 10. So, we get 200 cm cube per second. Now, moving to question B. Calculate the rate of which the radius of the tank is expanding when its radius is 50 cm. So we know that the volume of a sphere general formula is 4 over 3 pi r cube. By differentiating it to the t, we get 4 pi r square dr dt. Thus, we know that 200 is the dv dt. So we can conclude that 200 equals to 4 pi times 50 square. Thus, we can get that dr over dt equals to 0.00637 cm per second. Now, let's finish our calculation with question C, which is determine how fast the internal surface area of the tank is increasing at the moment when its radius is 50 cm. We know that the formula for surface area is 4 pi r squared. By differentiating it with respect to dt, we get 8 pi r dv dt. So, by inserting the variable that are known, we can get that 8 pi 50 times with 0.00637. We get 8 cm square per second.
Okay, I will explain to you about the discussion. So, this study used related rates to analyze how gas inflow affects a pressurized spherical tanks. There is three key rates were calculated. So, the first is the rate of volume increase, which is dV over dt equal to 200 cm cube per second. Next, the rate of radius expansion, which is dr over dt equal to 0.00637 cm per second at radius of 50 cm. So the last one is the rate of the surface area growth, which is dA over dt equal to 8 cm cube cm square per second. So, these results show that even with a large increase in volume, the radius can expand slowly, which is important for ensuring the tank can handle pressure safely. The increase in surface area also are critical as it affects heat transfer and structural integrity. So, these findings highlight the importance of mathematics in engineering, allowing prediction of how a tank responds to pressure, volume change, and also material limits. In real-world application, further studies should also consider material elasticity and temperature change. Overall, related rates provide a valuable insight for a safe and efficient tank design.
Lastly, I'll present about the conclusion. This study applied related rate to analyze change in the pressure spherical gas tank, focusing on gas volume, radius, and surface area over time. The finding highlight the importance of monitoring inflow rate, optimizing tank design, and considering structural and thermal stress. It demonstrates how differentiation aid in solving a real-world engineering problems and support safe, efficient gas storage system design. So this is all our reference for this project. This is all from our presentation. Thank you. Bye.